Hello and welcome to my channel. In this video I'm going to give you some information about the difference between distance vector, path vector and linked state protocol. So if you have not subscribed to my channel, hit that subscribe button. Also there is a bell button here. If you click on that, anytime I post a new video you are going to be notified, and also give me a thumbs up. That's going to encourage me to create more videos of this type for you. Okay, what is the difference between different types of protocols, and specifically what are different types of protocols? I'm going to speak about 5 different types of them. One of them is going to be, 2 of them of course are going to be distance vector, and they are REP, which is obsolete but still you use it in lab or some other places, and EIGRP. Of course they are a little different from each other, but they are going to be considered distance vector. I have one path vector protocol, and that's going to be BGP only because we do not have EGP, that was obsolete. And also I have 2 linked state protocols. They are going to be OSPF and ISIS. And which one is more common? Here is going to be EIGRP. From here we have OSPF, and also BGP is very much common. So let me just move this a little bit up because for some reason it just moved. And then let's go back to these protocols. Okay, so what is the linked state what is the distance vector protocol? First of all, let's say that these are my routers. And let me choose a better color so that I can write it and you can see it. And let me choose this one that is dark enough to be seen here. So let's say that I have these routers here, 5, 6, 7, 8, and they are connected somehow to each other. We can have it full mesh or we can have partial mesh. Doesn't really matter. I'm going to say, for example, these are the types of connections that we have here. And also this is going to be like this, and let's say that this one is connected to router 7 as well. Okay, distance vector protocol is going to use some factors to understand how it can reach to this network down there. So let's say that this is going to be a network 10, 10, 10, 0, and that's going to be /24. For some reason I had to write it like this. So how am I going to get to that part of the network? I'm going to use hop count if I am REP, or I'm going to use some other let's say criteria. Hop count says from router 1 to get to the destination I'm going to count the number of routers. So it says that there is 1 here, 2 and 3. This means I am 3 hops away from my destination if I just go this way. If I go this way, 2, 3, that's going to be 3 hops. If I go this way, 1, 2, 3, 4, that's going to be 4 hops. If I go this way, 1, 2, 3, or let's say not this one, 1, 2, let's say 3, 4, 5, that's going to be 5 hop count. So hop count is going to be used for REP. For EIGRP, it's going to say, okay, from here to the destination, I'm going to say this is the amount of delay that I have. This is 10, this is 10, let's say this is 10. If I go this way, the delay is going to be 30 milliseconds, and also I need the bandwidth. If the bandwidth, the lowest amount of bandwidth on the path to the destination is going to be important. So if this is a 1 gigabit per second link, and this is 1 gigabit per second link, and this is half a gigabit per second link, then the overall bandwidth is going to be half a gigabit per second because that is the lowest amount of bandwidth. So I'm going to say half a gigabit per second, also 30 milliseconds of delay. That's going to be put in a calculation, and that's going to give me a value. And I'm going to do this calculation for all the possible paths to the destination. Now, something that is very important to understand about distance vector protocol is they do not know what is beyond the neighboring router. So router 1 only knows about router 2. Router 2 knows about router 1 and neighboring routers, router 7, router 4, that's it. And they're going to retrieve some information. This means that I only know about the connected links to me and my neighboring router. My neighboring router is going to receive information from its neighboring router, and that is going to give me the information, and based on that information, I only know where the network resides. I don't know how to get to that network. I only know that I need to send it to the neighbor that advertised that network to me. That's all. So, distance vector protocols know about their neighbors, except RIP, of course, and they know how to calculate the metric to the destination based on the information that they have received from their neighboring router. That is the most important part. What about link state protocol? About link state protocols, I need to draw something. Let's say that I am going to put all of these routers in one area. Area is a concept that link state protocols use, and in this area what they do is they send information to their neighboring routers, very similar to distance vector protocols, but they are going to send information about themselves as well. So router 1 is going to say, this is the link that is connected to me, this is the link that is connected to me, and I am this. So if I check the database here, what I'm going to see is this. Router 1 is going to say, okay, my ID is 1111. You should know that I am connected to network 10.1.1.0/24. So this information is going to be sent to all routers. Any router which is receiving this information is going to be responsible to send this information to its neighbors, which are in the same area, in full. Which means that router 7 is going to know that there is a router 1111 in the network, which is connected to 10.1.1.0. Now, based on the information that router 7 has received, it's going to draw a topology in its memory. And it is going to have this image of the whole area. And it is going to say, okay, based on the information that I have, if I ever want to get to that part of the network, now I know the map to that part of the network. And I'm going to do this in this fashion. So, link state protocols are going to send information about themselves and the links that are connected to them. Other routers are going to receive that information, and they are going to calculate a map. Based on that map, they are going to decide how to send information to the specific network. Now let me change this a little bit. I assume that all routers are inside one area. That is the best practice. Most of the time you should make sure that all routers are in just one area. Why? Because nowadays routers are very strong. They have a lot of memory. They can easily calculate everything, and when they are in the same area, they have full information about the network, so that's going to give them the best optimal path to the destination. What if we have some requirements that says some of the routers should not be put in the same area? Then I'm going to have multiple areas. Maybe I want to say this is a branch, the router should not have all the information about my whole network. Maybe I have some routers that are not strong enough to process all the information, so I'm going to put them in another area. So what I'm going to say is, okay, this is one area, and I just call it area 0, and I have this part of the network in another area. And you can see that some of the routers are common. Let's say this is area 86 or something like that. Some routers are common between two areas. You should say that some of the interfaces belong to one area. For example, this interface belongs to area 0, this interface belongs to area 0, but this interface belongs to area 86. This belongs to area 86. And also the link between 4 and 8 should be treated the same, but let me just erase it. I don't really want it to be here. And that's not a clean removal, but whatever. Okay, so if I have such a topology, what is going to what kind of information is going to be sent inside an area and between areas? Inside an area, all the routers have full information about each other. So router 5 knows completely about router 3, router 1, router 4 and 2, every information about them, even router 7. In area 86, router 6, 8, 5 and 7 know everything about each other. Router 5 and 7 of course are going to have extra database information because they are connected to 2 different areas, but these 2 routers, router 5 and 7, which are, by the way, area border routers, they do not send complete information about each area to the other area. What they do is they are going to send just a summary of the data, and this part is very, very similar to distant vector protocols. So inter-area we act link state. Inter-area we act distance vector. So intra-area it is link state. Inter-area we act as let's say a distant vector. So that is what we have in here. So there are 2 link state routers, as I told, routing protocol, as I told you. One of them is OSPF, which is more common, but of course it is more complicated, and the other one is ISIS, which is less complicated but less common. For some reason some administrators are afraid of just approaching ISIS. I love it, but a lot of people don't. So OSPF is going to be the more common one. Okay, what about the path vector? Path vectors are a little different. Now let's say that these are not routers. These are just some autonomous systems. And by autonomous system I mean this is a company, for example. And maybe inside the company we have multiple autonomous systems, but I just assume that each one of them is a company and each one of them has, I don't know, thousands of routers inside them. But what we have is this kind of a connection between the companies, and some of their routers are going to act as the neighboring routers. The other routers are not going to, participate in this kind of a topology that we have drawn here. Now this means that each one of them are very separate from the others, and the only commonality that they have is the link between them. So I'm going to call this autonomous system number 1, this one is number 2, this one is number 7, this one is number 8. And to reach to this side of the network, what I'm going to do is to go through different autonomous systems. Now in this case, instead of calculating some information such as metric, I would say, okay, I'm not so sure what is happening inside this autonomous system, so I cannot really use metric value. But I know that there is an autonomous system on my way to the destination. So I would say, okay, instead of metric value, I'm going to just say which autonomous systems I have to go through to get to the destination. Okay, I would say that from autonomous system number 8, which is connected to this network, if this is advertised to me, that is going to be advertised like this. I would say this is 10, 10, 10, 0/24 plus some other information, of course. This is originated by autonomous system number 8. I have to go number 7, I have to go number 2, and then it is going to be me, which I'm not going to add it, of course, here. So I would say to get to 10, 10, 10, 0, I have to go through this networks, 2, 7, 8. So that means I have to go through 3 different networks to get to the destination. Now, what about others? I have some other paths to destination as well. I might go to from 1 to 2, from there to 4, and then to 8. So that's going to be like this: 8, 4, 2, 1. So I'm going to say, okay, 3 autonomous systems up here, 4 autonomous systems down here. Which one is preferred? I'm going to use this one. This is the best path to the destination. What if the links between these 2 autonomous systems are slow? What should I do? In that case, what I'm going to say is, okay, there are some attributes which I'm going to change. Other routing protocols do not have these kind of attributes, but I do. So what I'm going to say is, I'm going to use that attributes to say, okay, this link is faster, although the number of autonomous systems that I have to go through to get to the destinations are more, but this link is better, so I'm going to use this. Or I might say, okay, this ISP, this service provider, charges me less if I go through this network, but if I go through this, I'm going to have to pay more money. So what I'm trying to do is choose the best one, so I have to just manipulate the attributes in a way to that I can get to the destination through the best path. So path vector does not count on metric. It counts on the number of autonomous systems mostly. Of course, there are some other features that we need, there are some other criteria that we need to consider, but these are the overall understanding that you need to have from a path vector protocol. So let's summarize and have a wrap up. The distance vector protocol calculate the metric based on some values. They do not have any information about what is happening beyond the neighboring router. Path vector link state protocols have full information of all the routers, whether neighboring or not, inside their area. Outside the area, of course, they are going to receive some summary information, so they know where the network resides, and they have a full map of the area in their memory, or at least they create it. Path vector doesn't have information about inside the autonomous system. It just knows that it has to go through some of the autonomous system and get to the destination. So that is the difference between these routing protocols. Now, which one is suitable for you? You can choose based on your requirements, and I'm going to speak about these requirements in a separate video. But you should know that RIP is kind of obsolete, so this is going to be out of the equation. EIGRP is very good inside your network, but of course you cannot really go beyond a number of routers. That's going to increase the size of the database, and that's going to, slow down your network a little bit. And specifically, there are some cases that you need to consider when a route, for example, is not accessible. Then EIGRP routers are going to start searching for a better path to the destination. In case they don't have it, they are going to stay in that search forever, which is called stuck inactive. If you are working with a very huge network, then you want to create some segments, segmentize the network, then BGP is going to be very good. For other types of protocols, if you do not really want to go with EIGRP, OSPF and ISIS are going to be very good and very scalable. And of course, there are some other criteria that makes them suitable for your network. I'm going to talk about this in a separate video. So that's going to be this, and I hope you like this video, and I hope to see you in other videos.